Welcome to the HKS Energy Policy Seminar. I'm Joe Aldi, and I'll serve as the host today. As you know, we'll be doing this in a hybrid format. Pleased to have students and colleagues joining us here in the room, as well as having our friends, alumni, and some students who can't join us in person joining us on Zoom. A quick announcement about the schedule before we get started with today's talk. As you know, with the snow last week, we had to cancel last week's seminar. Richard Sandor, I'm pleased to say we have rescheduled for March 23rd. So I hope you can join us for that. That'll be a fireside conversation I'll be doing with Richard on the 23rd. Today, we're thrilled to have our colleague from MIT, Maria Zuber, here for her talk on groundwater, hidden reserves, public decisions. Professor Maria Zuber is the E.A. Griswold Professor of Geophysics and Presidential Advisor for Science and Technology Policy at MIT. Previously, she served as Vice President for Research at MIT for more than a decade, where she was responsible for research administration and policy, research relationships with the federal government, and oversight of MIT Lincoln Laboratory and more than a dozen interdisciplinary research laboratories and centers. In that role, she led the team that developed and provided oversight for MIT's Climate Action Plan. She has served on several presidential boards and commissions. Most recently, she served as co-chair of the President's Council of Advisors on Science and Technology, also known by its acronym PCAST. Maria, welcome to the Energy Policy Seminar.
Okay, can you hear me? Okay, great. Okay, so I'm happy to be here, and today I'm going to talk a little bit about groundwater, and let me tell you how I got interested in this. When on the President's Council of Advisors on Science and Technology Policy, we decided that water availability, and at the time we were thinking about drinking water and agriculture as being the real tensions for groundwater, and we were wondering if we should study it, and I'm going to talk a little bit more about how PCAST works in the talk, but we did wind up doing a study on groundwater, and I just spent an unbelievable amount of time just learning things about groundwater. And I just hate for all that learning to kind of go to waste. So I said I should do a talk on this. And so this talk, it's going to have three parts. Okay, the beginning part of it, I'm a geophysicist, and I actually study gravity and topography. And believe it or not, one of the main methods to determine groundwater movement and changes in groundwater is the exact same technology that we use to map the gravity field of the moon. Okay, and so I'll talk a little bit about that. Then I will talk about the groundwater study that we did as part of PCAST, so that'll be the part of the policy part of the talk. And then since the time we've written this report, it's now all about data centers. The questions about data centers are looming large, and I know you had a talk recently, whether last semester or what, about grid issues associated with data centers. I'll tell you, I quite frankly don't think that the groundwater part of the issue when citing data centers has been getting the respect that it deserves. Okay, and so I'll talk a little bit about that, and then what the challenges are and what some of the sort of policy issues that we should be thinking about. Just some of the information that we need in order to develop sound policy on data center sightings. Okay, so I know that there are people in the room and online who know way more about groundwater than I do, but I also know that there are people who don't know anything about groundwater. So I'm going to spend just a little bit of time level setting and talking about some nomenclature just to frame this for you. So water underground is a. Let's see. Do we have a pointer somewhere? Oh, okay, that's too bad. All right, well, I'll just point. Okay, so aquifers are places underground where the rocks are either porous or fragmented, and they have the ability to store water. Okay, and this is a cross section, cartoon of a cross section, and here is an aquifer, and at the top of this aquifer is a rock layer that is impermeable, which means that water can't get through on a any sort of a reasonable time frame, and so we call this a confined aquifer, and then above that we've got another aquifer, and it's got dirt on top of it, which of course is very permeable, and this is an unconfined aquifer, and we sample aquifers using wells. Okay, so just to put the context of what groundwater is used for, groundwater supplies about half the drinking water for the U.S. population, and 70% of groundwater use is used for irrigation. This needs to be updated for what data centers are using. It hasn't been updated yet, but it may wind up to be significant, or it certainly will if we don't. So over on the right-hand side here, these circles, the gold color is the groundwater. So that's the water that's held in aquifers. And then surface water is the water that's on the surface, lakes, ponds, estuaries, whatever, that are fresh water. And the sizes of the circles tell you the relative amounts. And over on the right-hand side there, you see some numbers and megagals. What is it? Mega gallons per day in terms of extraction. And so much of our agriculture in the Western U.S. Uses groundwater, and you as a consumer, the lettuce on your sandwich, you are using groundwater from the Western United States as you're eating your sandwich. And then obviously the security of the groundwater system and its sustainability is critical for health, the economy, and food security. Okay, this is a little bit of a busy chart, but this shows examples of some of the wells in the U.S. associated with different aquifers. We can actually determine how old groundwater is. Okay, and we can measure carbon-14 dating, the same way that use archaeological artifacts, tritium concentrations, chlorine-35. There are a variety of radioactive elements that decay, and we can actually tell when the groundwater got isolated from the surface water system. Okay, and this diagram shows that many wells extract water that's older than 100 years, which means that groundwater got isolated from the surface water system 100 years ago, and some are actually a lot older, and that turns out to be problematic. Okay, so some deep wells tap into fossil water. Okay, and fossil water is non-renewable groundwater that is from deep underground aquifers that have remained sealed from the surface for thousands of years, and in some cases back to the end of the last ice age, which was 11,700 years ago. So that showed you the previous chart. Now the thing about fossil water, the conditions that existed at the end of the last ice age are much different environmental conditions than we have now. The world was a lot wetter. There were kilometers of ice over the surface of much of North America, and if we're accessing fossil water, that is not going to be renewed on human lifetimes. Okay, it may renew very, very slowly, but it's not going to be renewed during our lifetime, and so that is actually a matter that is a big worry. Okay, because we often don't think about we think about groundwater as an economic resource. We don't think about it as a limited resource. Okay, that's going to stop, and we would probably price it differently if we did. So, these are three diagrams that show deep wells that tap into fossil water at greater than 100 meters, greater than 200 meters, and greater than 300 meters, and so it just gives you a sense that in some places in the U.S. We tap into fossil water. Here are some estimates of groundwater extraction, and this is for the year 2010. This is basically determined from wells, and so if you look at groundwater extraction and you can make an estimate of how much groundwater is there, which I'm going to talk about in a minute or two, you can actually do estimations of what is the usable lifetime for certain aquifers. Okay, how long are you going to be able to use it before they go away? And areas that are brown are below the minimum threshold. Gray means data is unavailable. Red means there's less than 25 years left to go. Okay, so there are places that if they're not in water stress now, they will be in water stress within the coming decades. Okay, so that everything that I showed you there was based on well records. Okay, and now I want to talk a little bit about satellite measurements. So I was back probably in the early 2000s. I was on a National Academy committee to look at Earth gravity from space, and usually National Academy committees review what's known, but this Academy committee, I think we actually won an award because we did original research that wound up as several scholarly publications that showed that we could now measure gravity well enough in order to detect small changes in movements of things on the Earth, okay, of which groundwater movement is one of them, okay, and it was that report that actually led to the Gravity Recovery and Climate Experiment, or GRACE mission. Okay, now to measure gravity, here's your gravity lesson for you. Gravity has units of acceleration. Okay, and acceleration is just a change in velocity, and velocity is just a change in distance. So you basically just have to measure a distance change and differentiate it twice, and then you get gravity. Okay, so it turns out that you can measure velocity from the Doppler shift. So if you have an ambulance that's speeding towards the emergency room, you can hear how the frequency changes as it goes by you, okay? And that you can actually measure how fast the ambulance is going from looking at the frequency shift on that. So, so if you can measure frequency shifts, then you can measure velocity. So, so it's incredibly simple to measure gravity in principle. And but if you want to measure it well, it's kind of complicated because you have to make corrections. So this is an example. GRACE is a satellite-to-satellite tracking mission. And what happens here, you've got two satellites that are chasing each other in orbit around the Earth. So they're in a polar orbit, 89 degrees. And as one satellite goes over a mass, there's extra mass there. So there's a greater gravitational attraction. And actually this thing, it gets pulled and the front satellite speeds up, okay? And it increases the distance between the first satellite and the second satellite. And then this one goes past it, and the behind satellite catches up, and that gets accelerated. And so it's like an accordion, okay? And the masses, they can be at the surface or they can be underground. And so what you've got to do is correct for all the mass that's on the surface, and then the mass that's left is underground, and that is often groundwater. Okay, so that's the way that it's done. Now, GRACE actually was able to measure. So all you actually needed to do to track groundwater is measure the velocity change between those two spacecraft. Okay, and so simple. And so there is a complication, and first of all, the atmosphere, there's drag in the atmosphere, and the atmosphere causes a deceleration, which is actually a negative acceleration. So you have to account for atmospheric drag. So you can't put these really low into the atmosphere. You've got to be above most of the atmosphere. So GRACE actually orbited at 500 kilometers, and the resolution on the ground is approximately the height, okay, more or less. So that's so you get lots of data frequently in large footprints, and then you want to compare those against the wells. Okay, now GRACE had the ability to measure the velocity change between the two spacecraft to microns per second, okay, which is a millionth of a meter, which means the velocity change, it's 1/100th the thickness of a human hair per second, okay? And actually at the moon, we did 50 times better than that. So, so it's, but it's like playing in the sandbox if you compare it to gravitational waves. So, but that gives you a sense that it's a very straightforward measurement to make in terms of just the principle, okay? But it's a little bit challenging to make it in practice. Okay, so here's an example of GRACE data. So the state of California in particular is pretty enlightened in terms of using science and technology to help them out. So every week, GRACE provides a groundwater map of the Great Valley, okay, where much agriculture occurs, and so what you can see, the thin black lines going up and down are GRACE's measurement of the groundwater anomalies, okay, changes in groundwater, and the green corresponds to the uncertainty in those measurements. And so you get some seasonal changes, and then the blue trend lines shows when the groundwater is recharging. The red lines are droughts, Okay, and so this is from a period of 2004 to 2022. So, on top of the seasonal, you've got the rainy season from like October to April, and then the dry season over the summer. So those are the smaller scale wiggles, and so you can see the measurement of the recharges versus the net droughts. Okay, and then just to give you some sense that this is a valuable measurement and that it works, down here, the green corresponds to the GRACE measurements of groundwater anomalies, and the purple corresponds to the groundwater anomalies that were measured and averaged from wells in the Great Valley. Okay, so it actually works pretty darn well. Okay, and so the reason that I'm emphasizing this is data is important, and it is possible to measure what's going on in terms of groundwater extraction. And we should be measuring what's going on, and we should make that available to planners and to decision makers who are deciding whether or not to site data centers. Okay. I also need to make the point here that gravity follows something called Laplace's equation, which is a second order partial differential equation. And that's not important for you to know. But what is important for you to know is that partial differential equation has, and there are an infinity of mass distributions that can satisfy that equation. Okay, and almost all of them are physically unrealistic. Okay, you really need to know something about what's the density of the rock that isn't water, how fractured the rock is. So you actually need extra information in order to be able to interpret the data. But what's pretty straightforward to do is the satellite goes over once and then it goes over next week. Well, the rock hasn't changed that much in the week. What's changing is the groundwater. Okay, and so as a consequence of that, what GRACE has been super good for is measuring changes in groundwater as opposed to the actual total amount of groundwater. Okay, that's what it's valuable for. Okay, all right. So then here's a map of the United States from GRACE, and this is something that the Goddard Space Flight Center releases on a regular basis, and this is what I'll call a drought indicator based on. So what it does is it looks at the United States. This was done on January 26, 2026, and it's essentially what they call a wetness percentile. It shows you the deviation from average of what is expected on that date, okay, over the course of a year. Okay, so if it's red, it's drier than normal at that time of year, and if it's blue, it's wetter than normal at that time of year. So again, this kind of information is available. Now, I made this point a little bit before, but this is actually a good diagram that summarize it. So these are spatial scales. So this is square kilometers. So 10 million square kilometers, and here's the resolution of GRACE. So GRACE, by itself, can resolve major aquifers, not smaller aquifers. But down here, you've got wells, okay, down at the 10 square meter, 100 square meter scale. And I've showed you that where we compare GRACE with well measurements in a given area, they agree pretty well. And so a study recently came out that actually did a very nice job of comparing GRACE data with well data, and from the well data you see the bottom of the aquifer, so you do get an idea of volume. Okay, and this particular study used machine learning in order to estimate the full groundwater volume in the United States. So this is an example of an area where AI is helping you move across length scales. So you'd be seeing more studies than this. And you could bring in, ideally you want to bring in more and more data sets. You want to do surface moisture, from passive radiometry. You want to take other, measurements of lakes and streams. So there's a lot of data sets there, and AI can help with the data analytics of getting this together. So the message on this slide, and this is really good cocktail party piece of trivia, is that the estimated amount of groundwater in the United States is about 13 times the volume of the Great Lakes. Okay. So that's a pretty good estimate of what we know. Okay, so that's the background on the science, and now let me talk about the PCAST report on groundwater security. So all right, so PCAST, some of you are probably very familiar. Some of you may have served on PCAST. Some of you may have never heard it before, but the President's Council of Advisors on Science and Technology, it's a federal advisory committee that brings together people from science and technologists, from academia, and from business, not from the federal government, who advise the president on policy matters where it's important to have an understanding of science and technology. Okay, so the interesting thing is that PCAST reports directly to the president, and this is an external group of experts. There are 2 or 3 co-chairs. So one co-chair is the director of the Office of Science and Technology Policy. So John Holdren, when he was director of OSTP, was a co-chair of PCAST under President Obama, and under President Biden, Arthi Prabhakar was the director of OSTP, and myself and Francis Arnold were 2 external co-chairs from outside of government. And the idea behind PCAST is that this is a group of scientists and technologies from outside the government giving the president and nobody else independent advice. Okay, so this report doesn't have to be approved by any other federal agency. It is external advice reporting directly from the president to the president. Now, the best possible PCAST report, okay, gives a recommendation or recommendations to the president, and the president likes them. Okay, so the president then, and this recommendation instructs a federal agency to do something by a certain date. Okay, now the reason for this is, if the president tells Harvard to do something, Harvard might or might not do it, right? If the president tells industry to do something, industry might or might not do it. But federal agencies are part of the executive branch of the government. So if the president tells a federal agency to do something, it's supposed to be done. So then the interesting and challenging thing about groundwater then is that the federal government pretty much doesn't control groundwater. Okay, so federal governments have very limited authority to regulate groundwater. That responsibility lies with the states, who create and enforce their own laws. And the system for doing this is heterogeneous across the nation. And And this decentralized system has some value, and it allows states to address specific challenges and opportunities within their jurisdiction. But basically, the federal government doesn't have a say in this. Okay, so so why did we even think about studying groundwater? Because groundwater is important and it's an issue. And the question was, what could the federal government do given the limited jurisdictions? So, so I'm not going to say a lot about this, but just water rights in general, and this goes for both groundwater and surface water. They vary considerably across the United States. Where landowners have unlimited rights, where multiple landowners over a single aquifer have to assure, a sustained supply. Prior appropriations have to, in some cases, balance interests of senior appropriations, and then treated as a public property where the state administers. So it just varies greatly, and we haven't even here talked about the issue of water cleanliness and contamination, but the role of contaminants is an important issue that needs to be taken into account as well. Do you know that in Texas, if you drill a well and you horizontally drill into your neighbor's property, you can take that water? So, yeah, interesting. So there are farmers who have found out the hard way that was the policy in Texas. So, so what we did is we talked with well, the EPA, we talked with state agencies, we talked with the USGS, all kinds of subject matter experts, all sorts of state experts. We solicited public input, and then we held a workshop in Tempe, Arizona in July of 2024, and 200 people showed up in Tempe in July. So this tells you that people were very interested that something was coming down, and they needed to go defend their point of view, whatever that is. And so here are some of the things that we found. State and local efforts. A lot of these state agencies, they're just limited on the basis of funding. What they can do, they have limited accessibility to groundwater models and predictions. They don't know the data like many of us would be able to dig into the data. They don't have the background to be able to do that. The data sets aren't standardized, so there isn't interoperability of data sets, so it makes it challenging to share data and best practices. And a big issue that they don't have the hydrogeologists that they need to even be able to, even if they could hire, they don't have the talent that they need to be able to solve this question or do things better. So so what we decided to do on PCAS is to focus on the science and technology aspects of the problem, not surprisingly. How can the federal government help state and local water managers? What research is needed to safeguard water security and assure sustainability of groundwater? And then what are the potential incentives to provide sustainable quantity, quality, and efficiency? So, so there's two charts of recommendations here. Accelerate development of a comprehensive repository for data and toolkits for analyzing it, okay? Establish a research program to advance the technologies and strategies, okay? And then establish an incentive program and a network of engagement hubs that of course, include the tribal nations to support planners at all levels in sustainable groundwater use. Then a system of grants to incentivize planning, incorporate the valuation of groundwater resources into accounting for national capital. And then finally, what can the federal government do to encourage a skilled workforce? So it could be fellowships, say, for graduate work in water-related studies. Okay. So so now let's a few more charts here, and we'll talk a little bit about data centers. So so water has become as critical to data centers as electricity, and but often water comes from reservoirs. It can only be replaced by groundwater, and the usage often greatly exceeds the replenishment rate. So I've listed some stats here. For each kilowatt hour of electricity consumed, the data center needs 2 liters of water for cooling. Okay. When companies build data centers, they want to site them where they can get the cheapest electricity. Okay. They don't site them based on what the groundwater availability is. Okay. And data center operators don't disclose how much water they use. They often aren't required to disclose that. And then, so the consumption needs outpace the efficiency gains, even though there are gains being made in terms of cooling of electronics for data centers. The consumption needs are far outpacing that. And this one's pretty shocking. Local utilities are often prohibited from releasing data to the public about water consumption because the companies require them to sign NDAs. Okay, so so this is all obviously problematic. So I've made a list here about some policy issues that I think are relevant to groundwater siting and operation. So water availability. Is there enough groundwater to support long-term operations without depleting the reservoir? As I showed you at the beginning, we have a lot of information about groundwater that could be brought to bear. I mean, I went and I collected it from like all these sources, but it could all be brought together and made to be interoperable, and it could be put on a public database. We need to look at the competition among existing users. How do we prioritize during times of water shortages? There are cumulative impacts. Withdrawal can compound in the same aquifer. There needs to be transparency and disclosure, no NDAs on water usage. Okay. Then environmental impacts. You extract water, the ground subsides. There could be wetland impacts, flow contaminants, flow and dispersal of contaminants. Equity and environmental justice. The wealthier, more sophisticated areas get the best deals because they negotiate the best deals. Okay. Cooling technology choices. This is like a different talk, but there are methods that use high amounts of water and lower amounts of water. Water pricing externality. So groundwater is often underpriced. Okay, I mean, it's just priced to reflect energy usage, and it is not priced as a limited resource. Okay, so that is a big deal. And then the governance fragmentation. So the governance of groundwater, it often involves districts, states, environmental regulators, land use planners. I mean, it's all over the place. So there just isn't a consistency on how this is done. Okay. And then, so this is my last chart, and then we'll open it up for discussion. So the major tension here is short-term economic development in areas versus long-term water security. Okay, and I mean, you all know not a lot of people work in a data center. Okay, but they could be paying millions in taxes of tax revenue. And the planners want that tax revenue because they're dealing with shortfalls. Okay, so if the water usage is high, they don't necessarily want to release the data on that. They're thinking short term. Okay, now if they had a conscience, maybe they would. So think about the basin scale inventory, public disclosure. There's got to be operational plans for drought conditions. I don't think data centers want to stop operating when there's a drought. They probably have agreements that they have that written into agreements. We need independent monitoring of groundwater use and reporting of groundwater use, and then a clear definition of what a sustainable yield is. Okay, and then this is a, last month in Forbes, there was an interesting opinion piece saying, should U.S. data centers be treated as strategic infrastructure as opposed to a local real estate project? And it's a very interesting question. It would give the government, the federal government, a larger role. And I can tell you, there would be no interest in that from local entities whatsoever. So really interesting question, but it would be a tall hill to climb to get buy-in from all the stakeholders that I talked about. So I'll end it there and then be happy to hear your questions and comments.
Great. Thank you, Maria. So I'll start with the first question before we open it up from the audience. And there's a few things here when I think about both the impacts of climate change on the groundwater resource and recharge. That it's interesting how it might affect potential demand among various users when we think about climate change. But I'm curious about tying together what I learned most of in this talk, which is how we actually measure groundwater, which I found fascinating, with this last part on data centers. So we've got sort of build out of data centers in the US clustered in about 4 or 5 regions around the country. We've got Northern Virginia, we've got Texas, I think we have the Pacific Northwest, I think we have parts of California.
Arizona too.
Arizona, okay.
Has a bunch, believe it or not.
Okay.
Arizona has a lot of data.
So I wonder if it's possible with the GRACE technology that you talked about.
Yeah.
Can we start to circumvent some of these information problems? The fact that there are these NDAs, we don't have good localized information. Is it possible to use GRACE to start to see if at these clusters we're having a material impact on groundwater?
Well, certainly you can do it at the broader scale. Okay, and then ideally you would want to GRACE works really well, but ground truth is fantastic. So ideally you would want to ground truth this against a well if you could. So if you couldn't, if you couldn't get the well close to exactly where you would want it, you put it as close as somebody's going to let you drill a well. Okay, there's going to be somebody who has land that would let you do a well so that you could, and you don't need lots of these. You just need to do enough, and it goes without saying you have to do like extra processing to do things at a regional level, but that there are people who know how to do those kinds of things, and we should train more. But it's yes, we could get at that, and there are people in this room. If you're looking for something really valuable to do, this is just a fantastic problem that brings together scientific knowledge and policy. So those of you who have those joint interests,
Great.
Yeah.
Let me turn to the audience for questions. Bill.
So thank you for this. This is terrific. I'd like to ask about a related problem, which might be different. So I'm not sure, but this is about hydrocarbons and how much hydrocarbons we have under the ground and all that kind of thing. And there's been this conversation which is going on for decades, which is we're about to run out of hydrocarbons. And it turned out when you look closely at that, the Geological Survey and other people like that were making very strong and implicit, that's the important part, economic and technological assumptions when they were defining how much stuff was there. It wasn't how many molecules are actually there. It was stuff that you could get out of the ground at reasonable cost. And we're running out of that, and that's good. I mean, it would be crazy if it weren't. But it turns out that the amount of actual stuff in the ground is enormous.
Oh yeah, well,
by comparison to what we're extracting.
drilling techniques have
Right,
improved
exactly.
hugely, and now actually the ability to do the horizontal drilling
Right.
is
So is
just
this,
extraordinary.
does this have a similar characteristic,
Yeah.
which is with technological change, drilling techniques, suddenly we would think, well, we have a lot more water.
We probably do. Okay. But but I would say the oil and gas, that was basically ferns and trees that died, back in the Triassic, and have been covered for hundreds of millions of years. Once you get down to lower crustal levels, the groundwater is actually less dense than the surroundings, so it gets hot and it kind of meanders up towards the surface. So I think you might want to use it for steam, but it's certainly, you are certainly correct that there will be more groundwater, and we have to. The question is making it cost effective to get it. Now, groundwater is underpriced. I mean, if you priced the resource on the basis of using these advanced techniques to get it, it would make their usage in data centers more cost prohibitive. So, or golf courses, yeah. Yeah.
Hi, I'm just curious. So what's the total we're taking out of deep water aquifers now on an annual basis? Do you know?
I don't know the number off the top of my head.
Yeah.
But
Okay, it was maybe a different question.
Yeah.
Where's it go? How much of it after it's been used is usable somewhere else, or how much is
Oh,
lost?
So you raise a good point. Okay, and actually, I think the answer to your question is on that chart that I showed right at the beginning. We could look that up. But you're correct about the possibility of water reusage. So Texas right now is starting to get with the program, and they are there's I don't think it has progressed to an actual regulation yet, but it's approaching that, of telling data centers that they need to use recycled waste, prioritize using recycled wastewater from hydrocarbon extraction in order to do data center cooling. And, well, obviously purified, but so there is some reuse possible. But there are different techniques, and evaporative techniques evaporate it, so that's not reusable until until it rains. Yeah, so should we, let me try to see if I can bring up this. Well, it looks like about 50,000 million gallons per day extraction. So multiply that by 365. Okay.
Yeah. So just
Yeah.
figure out at a very high level, how much of that 50,000 is essentially lost for downstream use after it's been used once? How much ends up in the ocean? The only way to get to it is to desalinate it. How much of it ends back in the ground? Do we know those numbers?
They're going to be very local, I think.
Uh-huh.
So I don't know it, but I think in any regional, if you want to do all of this regionally so that
Yeah.
you can really get a good inventory. And that is certainly measurable / modelable
Got it.
thing that could be estimated.
Great. Okay, thanks.
Yeah.
Hi. Earlier you mentioned that GRACE is good for detecting changes in groundwater. Is there something similar to like an excess death metric you could use?
To what?
An excess death metric from epidemiology studies. People will use these changes in death rates per year to estimate the effect of things like pandemics.
Let's see. I'm sorry. I'm not
Oh,
understanding.
sorry. The measure is called excess death.
Excess death.
Yeah, it's like comparing the total number of deaths from one year to another.
Yeah.
When one year there is no pandemic and the other there is.
Yeah. Oh, yeah.
Is
Okay.
there something like this you can do to estimate the effect of regional like data center usage?
In terms of the water has changed this much from year to year.
Or like the difference in the expected change year to year. It's like, let's say it changes 1% one year. And
I see what you're saying. Oh, well, yes, one could do that because you just, let's wait. Let us. Okay, so. Okay, so this chart, it's not exactly what you want, but it's kind of the same principle. So this shows you whether this is drier or wetter than normal on a given day. You could do that 5 years ago, okay, and figure out, what the groundwater changes in that time frame, and then you could do it after the data center had been there for some amount of time. And the measurement is extremely precise, so you can go, over. The whole thing about GRACE is that there's a long decades time scale on this that you could do. So you actually could do that study, and I'm not aware that it's been done.
okay, cool. Thank you.
Mm-hmm.
Thank you for your presentations. Very interesting. I had a question. You talk about how it's important to have a different price for groundwater. I was wondering if other country has some regulation to have a different price, or some state is working on that.
The answer is yes. Okay, and I'm not sure what the numbers are, but they're certainly, in some areas, like I know Virginia right now is really talking about we've got to start pricing this according to what how much we have and should there be different rates for data centers versus domestic use. So you're seeing this now play out with the grid and electricity, and companies being told that they should provide their own electricity. Well, if they got to buy the water, you could see where this is going, that maybe there should be a different price, and that would really inspire different cooling technologies. Like right now, the companies want to do this as cheaply as they could, but if there's a technology that used a lot less water, but it was more expensive to implement, if the price of water was such that it might make that more economical. So doing it incentive-wise as opposed to punitive-wise is always a better way to do it.
Yeah. Thank you.
I have a question about the data center. You mentioned that data center will use much more water. My question is, now, as far as I know, data center just use the air source heat pump to best their cooling. So I don't know if the water consumption is just a direct consumption, or it's just the indirect consumption of water, just because they use much more electricity. Electricity will be generated based on much more water consumption, or it's just used to water-based cooling. If it's just water-based cooling for data center, I think now the technology has developed, or maybe we can use less and less water for cooling. Yeah.
Well, there are air-cooled technologies. They're not quite as efficient, but there are also technologies that use fluids other than water for cooling as well. And, with jets that really focus the fluid on exactly where it's needed as opposed to more broadly. So there's ideas out there, and there's more ideas coming. So technology really, I think, can come to the rescue, but hopefully sooner rather than later. So.
I'd like to go back to the policy in the government area. And I think that one of the things that strikes me is you mentioned that the local and state governments don't have a lot of information, and that there's a role for the feds. I would argue that the states quite often don't have a lot of information. The locals are very struck by it. For example, in New England, you have areas, I notice in Maine, you have up here drought up there. Drought is defined in New England entirely based on fire hazard. It's not based on the amount of groundwater or the amount of water availability. It's entirely done on fires. That's not the case in the West, where it is done on groundwater. But the question I had is, if you wanted to do this, if you said, okay, we got to have a stronger role of feds, they got to put out at least an annual report, and they got to and provide information to local and state decision makers. Where do you put it in the feds, and where's the expertise?
In the federal government.
Federal government, yeah.
Actually, I'd give it to NASA.
Okay.
Because they got a lot of really great data analysts in NASA who are really adept at using this kind of data set. It could go to NOAA, but NOAA has such a significant operational responsibility that whenever there is an active hurricane season, all the funding goes to deal with the operational aspect of NOAA's mission, and not with things like this. So, but or you could put it in the USGS if they certainly have experience in hydrogeology and with the wells, but less so with the satellite data. But you could hire some satellite people in the USGS if it's Department of the Interior. So
that would be a good answer for the technical part of this. But I've also got to have an agency that can talk to and have a relationship with the people on the ground at the state and
well, that would be
level.
that would be the Department of the Interior would be a better place for this. I mean, I actually, thinking about your question a little bit more, NASA could produce the products and send them over, and they have perfectly capable people in the USGS who would be able to mesh them with what they have, and they do talk to the locals there. But I was really interested in your initial comment about the definition of drought. I mean, I would imagine, since this is a US data set, that they're using a consistent definition, but maybe not. That's
well, one, you could be totally correct on how this map was made. I'm just telling you that having basically been doing a study of the drought areas because of the potential water shortage, I found there was no water shortage, and the drought was entirely related to at the local and state levels to fire hazard.
Interesting. Wow. Well, being very clear about what's really going on would do a lot. So, yeah, fascinating.
You said you can date water with carbon-14 dating.
Yeah, or other. There are other ways to do it too.
Methods.
Yeah.
Is there any advantageous? Is there any is there any difference between old water, this fossil water, this new water, as far as how we treat it, how we consume it, how we water with it?
No, not the age by itself sort of doesn't matter. That the issue with the age is just, are you taking water that isn't going to be replenished this year or in our lifetimes? You know, you want to be, if you know, if they're pumping 10,000-year-old groundwater, you know, for drinking water in Phoenix, they got a problem, right? Okay, that's clear. It's the issue of the contaminants within the water that would really be the issue, but not the age of the water in itself.
So, Maria, I want to follow up on Henry's question about sort of how to think about engaging the federal government. You noted that a good PCAST report is one the president likes and can go tell an executive branch agency to go do something. And one thing that comes to mind, given how you describe the sort of policy landscape here, where to the extent there are authorities that are well established, they're established under state law, not under federal law. The analog that comes to, or an analog that comes to mind for me is how we think about like energy building codes. There's not a federal energy building code. It's done state by state.
Yeah.
But one thing the Department of Energy does is it works a lot with the states.
Yeah.
The Department of Energy has periodically established a model building code that states can adopt. But part of it is this kind of like back and forth. And I'm kind of curious, it doesn't strike me initially that NASA, NOAA, or USGS have that kind of strong relationship with states to be able to do this. So I'm kind of curious how we might be able to go into the states. You talked about how states have different rules for how they govern, how they might price, how they might regulate groundwater withdrawals. There's that potential for learning there, but how would we, you know, if the president were like, how do I actually make this happen? How do you actually go about getting that information from the states and learning and synthesizing and hopefully establishing kind of best practice that others can learn from and adopt?
Yeah, it's we talk to a number of state authorities. So any scientists that you talk to, they want help. Okay, they are willing to partner and say, give me the tools, help me with the tools so that I can do my job. You know, at the kind of regulation planning level, it's mostly go back where you came from, you know. But you know, so you would have no real pushback from like the scientists working in the state agencies in terms of providing information. They would love to have more information, but the uptake of that information as you go, you know, kind of higher up the bureaucratic chain as far as the approvals go, you know, so, you know, building trust, you know, is always possible, and but it takes a while, right? You don't go have one meeting and everything's great. So so building trust and having the federal government be a resource to help in planning, you know, that clearly it's going to take a while, but that's what it's going to take is personal interactions, I would say. And but certainly that's not going to happen, I think, soon. Maybe it'll happen in the future, but it's, you know, that's what it is.
Okay.
Yeah.
Great. Yep. One more question before we wrap up.
Okay. Yeah.
Thanks so much for the presentation. I'm doing my PhD here, and I'm actually studying groundwater use in Chile. And I think like the case of the US is interesting because you have like this very decentralized way of managing water, like across like all the different territories. And obviously in the West is so different from here in New England, etc. And one of the problems that I see in Chile is the lack of information. Like we have some data on wells and measurements across years, but it's very scattered data. And I think the water authority there is like granting water rights like there's no tomorrow, because if you can find water, you can then say like, okay, yeah, then you have a water right. In this case, like if we had a scenario of like perfect information about where's the water, how much water there is, and how much we're using, what do you think is the best method for regulating like how we give water to different types of users? And in the case of data centers, if you have kind of like, are you tapping from wells that are like privately managed, or are you actually like tapping into the utilities that then have to build that infrastructure? Yeah, how do you think about like, if we had the perfect information, how do we regulate water across like so many different territories?
Well, you certainly don't want to use the U.S. as a model. It's what I. I mean, from the standpoint of uniformity, you know, a centralized system is better, but you know, one that is trusted and in communication with folks on the ground. And you know, Chile has access to the GRACE data just like everybody else. So you know, hopefully you're using that down there as well. So
Yeah, no, totally. Thank you.
So before we wrap up, let me note that we'll meet again next Monday at noon. We'll be hosting Ann Finucane, former vice chair of Bank of America, for a fireside chat about energy and climate-related finance. And finally, please join me in thanking Maria Zuber for both the presentation today and for your service on PCAST. Thank you, Maria. That was great.
Thank you. Thank you.